Hi all, let's take a look at our first trigonometry section. In section 4.1, we're just talking about angles and radians measure and trying to get comfortable with some of the basics of trigonometry. So the things that we'll be doing in this section is we're going to be looking at the vocabulary of angles, talking about the initial side of an angle, terminal side of an angle, things like that. Talking about degree measure, and how degree measure is going to range from 0 to 360 around a circle, and then radian measure is going to range from 0 to 2 pi radians around a circle. So we'll be talking about those. Be able to convert from degrees to radians and vice versa. So we need to be comfortable with moving from one to another. That's going to happen quite often. We'll be able to draw angles in standard position, find coterminal angles, just meaning angles that end at the exact same value, then find the length of a circular arc, and then use that linear and angular speed to describe motion in a circular path. Okay, so first up, let's just talk about angles. So on this page, what I'm just talking about is that an angle is just simply formed by two rays. You can see I have here that they meet at the point B, where I have the ray BA and the ray BC meeting at this point B. Well, the angle between them is our definition of an angle. An angle is formed by two rays that have a common endpoint. One ray is called the initial side and one is called the terminal side. So in this case, the blue ray is my initial side and the red ray my terminal side. Now, this angle is moving in a positive direction. Positive direction for angles, it's counterclockwise. If it would be going in the other direction, that would be considered a negative angle. They always move, negative angles move in a clockwise direction. So first up here, an angle in standard position. The only thing I need you to remember about an angle in standard position is that the initial ray is on the positive x-axis. So an angle in standard position, if its vertex is at the origin of a rectangular coordinate system and its initial side lies along the positive x-axis. So then we can more clearly see what this angle is. Like in this case, I can say, well, I know this angle alpha is greater than 90 degrees because there's a 90-degree angle between the x and the y-axis. There would be a 180-degree angle if the whole angle fell, or if the terminal side fell on the negative x-axis. This is probably approximately a 120-degree angle because it's a little bit closer to 90 than it is 180. Now, I was talking about earlier that angles can go either in a counterclockwise direction or a clockwise direction. In this case, the angle theta would be a negative angle because it's moving in a clockwise direction. But either direction is absolutely acceptable. Now, that's what I was talking about right here, the positive angles and negative angles. Positive angles are just generated when you go in a counterclockwise rotation. Negative angles here, negative angles are going to be when you rotate in a clockwise direction. I need to wait before I go on to the next page. Now that next page. If I talk about a quadrantal angle, that's some terminology often used, and students say, well, what's a quadrantal angle? It's just where the terminal side is going to fall precisely on one of the values on the XY coordinate plane. So in this case, you see the terminal side is falling on the negative y-axis. That's a quadrantal angle. If it would fall, if the terminal side falls on the positive y-axis, the negative x-axis, or the negative y-axis, you have a quadrantal angle. Remember, your initial side of a standard angle is always the positive x-axis. Now, measuring angles using degrees. We can say, well, an acute angle is any angle that's measuring less than 90 degrees. A right angle measures exactly 90 degrees. Obtuse angles are going to measure between 90 and 180. And then a straight angle, or of course we just think of it as a straight line, it's going to measure 180 degrees. Now, if we're talking about measuring angles using radians, this is something a lot of students don't get when I say, what is a radian? And they're like, gosh, I don't know. Well, a radian is just the distance it would, or the angular distance it would take for you to put the radius on the surface of a circle. So if you're thinking about the circumference going around a circle, the angular distance it would take you to put the radius on the circle is the angle it would take for a 1 radian angle. Now, we know that the distance all the way around a circle is 2 pi radians. So that means that you could approximately put 6.28 radius lengths across that circle all the way around. Now, that leads us to our definition here. An angle whose vertex is at the center of the circle is called the central angle. The radian measure of any central angle of the circle is the length intercepted of the arcs divided by the circle's radius. So I'm saying that the radian measure is the distance on the surface area distance on the circle divided by whatever the radius is. That's going to be the radian measure. Now, this would be a radian measure of 1. This is what I was talking about on the previous page. A radian of angle 1 just represents the angle required for you to be able to fit that radius on the surface of the circle. So imagine that radius is some type of like a string or something that can bend to the curvature of the surface of the circle. So if that's the case and you took that same distance r there and put it on the surface of the circle, well, then this angle at which that happens is going to be a 1 radian angle. Now, so radian angles actually have a meaning, whereas degrees, they were just created to be convenient. When somebody says, well, what is a 1 degree angle? Well, it's just 1/360th of a rotation of a circle. Other than that, it doesn't really get its meaning from anything. Now, a radian measure. If we talk about, if I say consider the arc length of distance s here on a circle of radius r, the measure the central angle theta that intercepts the arc is, well, this just goes back to what the whole definition of a radial length is. I can say, well, any angle there is just the arc length that you have divided by the radius. So in this case, if I said, how many radius lengths could I fit on the surface of this circle over this distance s? Just by looking at it, I would estimate 2. So I would estimate here that theta is a radian angle of 2 radians, and I guarantee you that's pretty close there. If it were a straight line all the way down, it's pi radians, which is approximately 3.1415. Now, if I go to the next page here, first example, it says computing radian measure of an angle. It says a central angle theta in a circle of radius 12 feet intercepts an arc of length 42 feet. What is the radian measure of theta? So imagine this last problem where that red distance on the surface of the circle is 42 and your r value here is 12. Well, you'd say, well, okay, then your angle theta is just going to be the surface area on the circle s, 42, divided by the radial length, 12, and we can see that that would be a theta value of 3.5. The radian measure of that angle theta would be 3.5 radians. Now, if I wanted to convert that radian angle to a degree angle, then I just use the equivalency. So halfway around a circle we call pi radians, or 180 degrees. So if I'm going to convert from degrees to radians, I just have to remember, well, then I have to divide by degrees and multiply by radians. So then you multiply by the fraction, pi radians over 180 degrees. If I need to get rid of degrees and put my equation in terms of, sorry, if I needed to get rid of radians and put my equation in terms of degrees, then I would need to divide by radians multiplied by degrees. So you see I multiply by the fraction 180 degrees over pi radians. Now, let's look at some examples of that. So I start off with 60 degrees here, and I say, I want you to tell me the equivalent radian measure. No problem. So 60 degrees, I know I'm going to divide by 180 degrees, multiply by pi radians. You'll see I've just canceled out the degree sign here to show, yes, the degree notation does cancel. That's going to give me 60 over 180 times pi. And this answer is going to be in terms of radians. Well, 60 over 180 reduces down to 1 over 3. So I can say, well, this is just pi over 3 radians. Now, whenever you're putting your final answer, if your answer is in terms of degrees, you must put that degree sign. If your answer is in terms of radians, you don't have to put it. So I put it here, but if I just put pi over 3 without writing radians beside of it, it's implied to be in radians. So please keep in mind, you can always write radians, but if you don't write anything, it's assumed to be in radians. Now, that's kind of convenient if your answer is supposed to be in radians, but what if you're putting an answer that's supposed to be in degrees and you don't put anything after it? Then it's wrong, because the reader is supposed to assume it's in radians. So degrees, you have to put the degree sign after it. Radians, you can if you want, but you don't have to. So here, converting 270 degrees, I can say, well, I'm dividing by 180 degrees, multiplying by pi radians. That gives me 270 over 180 times pi. Well, 270 over 180 reduces down by a factor of 90 to 3 pi over 2. And again, you can put the radians or not. What if I have a negative degree? No big deal. I just say, well, that's just going to be negative 300 degrees. You're going to divide that by 180 degrees, multiply by pi radians, which gives me negative 300 over 180. And then here I reduce down 300 over 180 by a factor of 60. 60 goes into 180 3 times. 60 went into 305 times. And of course, you still keep your negative for negative 5 pi over 3. Next example here, I need to go the other way. Well, what if I have my answer or my term in radians and I need my answer in degrees? So I can say, well, all right, if I'm converting 2 degrees and I start with radians, I have pi over 4 radians. So I need to get rid of radians. I divide by pi radians, multiply by 180 degrees. And when I do that, I can say, well, that's just going to end up being 180 degrees divided by 4. I can see that the pi canceled out of this problem. 180 divided by 4, it's going to be 45 degrees. And again, please do remember, degree sign must be on your final answer. If I have negative 4 pi over 3, well, I take that, I divide by pi, multiply by 180. You say, well, that's just going to be negative 4 times 180 degrees over 3. I think of that as 180 over 3 is 60. 4 times 60 is going to be 240. And of course, I keep the negative sign and the degree sign up here. If I have something like 6 radians, so notice the pi isn't in there. So anytime you have a radian answer and it's got the pi already in it, you're probably going to get a nice degree answer. It's going to be a whole number degree. But if it's not in terms of pi, you're going to get an irrational degree answer. So when I'm saying how many degrees is 6 radians, well, 6 radians is approximately all the way around. 2 pi radians, which is 6.2857 radians, would be 360 degrees. So I know this is going to be a little less than 360. So when I go into it and I figure out, I can say I can still simplify whether there's a pi there or not by multiplying by 180 degrees over pi. That gives me 6 times 180 degrees, but this time I'm still dividing by the pi because there was no pi to cancel it out with. So I just go to my calculator, 6 times 180 degrees divided by pi, and that's going to approximately give me 343.8 degrees. Now, drawing angles in standard position. If I say the figure below illustrates that when the terminal side makes 1 full revolution, it forms an angle whose radian measure is 2 pi. So that's all the way around, you get 2 pi radians. Now, the figure also shows the quadrantal angle. So what if I want to go 3/4 of the way around? Well, you say, well, 3/4 of the way around, that'd be 2 pi times 3/4. And you say, well, that's at 3 pi over 2. What if you want to only go half of the way around? Again, please remember the entire distance around is 2 pi. So half the distance around is 1/2 times 2 pi. That's an angle of pi. And of course, if you just have the angle formed by the positive x and positive y value, that's going to be pi divided by 2 for pi over 2 radians. So remember, 90-degree angle, pi over 2, 180-degree angle, pi. This would be a 270-degree angle, 3 pi over 2, and 360-degree angle for 2 pi. Up next, if we talk about drawing angles in standard position, so if I say draw and label the angle in standard position, and I give you theta is equal to negative pi over 4, well, just based on the last page, you'd say, well, pi over 2 is straight up. So if I cut that in half, pi over 4 would split quadrant 1. Pi over 4 would be right there. Well, in this case, pi over 4 would be up here, but this angle is negative pi over 4. So the initial side of my angle is always the positive x-axis. I go pi over 4 radians in a in a counterclockwise direction, negative angle, positive if you think about direction around a clock. So I can say, well, it's just half of a quadrant this way. Negative pi over 2 would be straight down. Negative pi over 4 splits quadrant 4 in half. That would be my angle. Now, if I look at my next problem here, 3 pi over 4, well, please notice it's a positive angle. So you'd say, well, each pi over 4 is going to split a quadrant. 1 pi over 4 would split quadrant 1. 2 pi over 4 would go straight up. 3 pi over 4 would split quadrant 2. So I could say, well, okay, an angle of 3 pi over 4 is going to look like that. What if it said 4 pi over 4? You'd have a straight line, the positive x and negative x-axis. 5 pi over 4, the terminal side would be in quadrant 3, and it would be splitting this. 6 pi over 4 is the same thing as 3 pi over 2. It'd be straight down. And then finally, 7 pi over 4 would be splitting quadrant 4 over here, and your angle would be this initial side. Now, if I say, well, what about a negative 7 pi over 4? You just say, well, all right, you're going to be rotating in a clockwise fashion. And I know 8 pi over 4 would rotate all the way back around because 8 pi over 4 is the same thing as 2 pi. This isn't rotating quite that far. It's 1 pi over 4 short of a full rotation. So you say, well, okay, then it's going to split quadrant 1 as it goes around. This would be negative 1 pi over 4, negative 2 pi over 4, negative 3 pi over 4, negative 4 pi over 4, negative 5 pi over 4, negative 6 pi over 4, and then when we go to quadrant 1, we get our negative 7 pi over 4. When we're looking at 13 pi over 4, okay, so what we're going to have to do in that case, and my little arrow here doesn't show it too well, if you think about rotating all the way around, that's a rotation of 2 pi. Well, 2 pi is the exact same thing as 8 pi over 4. So then, after I know I've had to rotate 8 pi over 4 to get back to this positive x-axis, 9 pi over 4 would put me in the mid part of quadrant 1. 10 pi over 4 would put me on the positive y-axis. 11 pi over 4 would put me at the midpoint of quadrant 2. 12 pi over 4 would put me at the negative y-axis. Finally, 13 pi over 4 puts me at the midpoint of quadrant 3. So now you might say, well, hey, 13 pi over 4 is the exact same thing as 5 pi over 4. Yes, we're going to be talking about that in just a second. They're called coterminal angles. So since 5 pi over 4 and 13 pi over 4 end at the exact same point in our XY quadrant, you say they're just coterminal angles. They have the exact same terminal side splitting quadrant 3. Now, this just shows you some angles within the unit circle. You should be familiar with every single one of these angles. Please notice each quadrant is split up into halves and 2/3, and we need to know both their degree and their radian angle measure. So if we know straight up is 90 degrees or pi over 2 radians, as we've been doing, if you cut that in half, then in radians, it's pi over 4, just like the last problem, we had to add pi over 4. So we said 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and so on. We went all the way around and said, well, this angle right here, it's the same thing as 13 pi over 4, because you could say 5 pi over 4, and if you added another circle revolution around that, it would add 8 pi over 4, same thing as 13 pi over 4. So we need to be comfortable with all these angles, and I was talking about the angles halfway through, but we can also look at the angles a third of the way through. You could say, well, what if I split pi over 2 and a third? Well, pi over 2 divided by 3 is pi over 6. What if you go 2/3 of the way through that quadrant? Well, it'd be 1 pi over 6. This would be 2 pi over 6, which reduces down to pi over 3. This would be the same thing as 3 pi over 6. Here we have the same angle as 4 pi over 6, 5 pi over 6. This would be 6 pi over 6, 7 pi over 6 here. And this 4 pi over 3 is the same thing as 8 pi over 6. You could keep on counting by pi over 6s all the way around. Now, the only thing I've done here is show that it can also go in a clockwise direction as long as you consider these angles are negative in that direction. So now, if we look at where an angle is 1/12 of a revolution, you just need to remember that a full revolution around a circle is 2 pi radians. So if it's 1/12 of a revolution, well, then that's the angle pi over 6 that we were talking about. And that should make sense to you because pi over 6 is 1/3 of each quadrant. If you have 3 of them in each quadrant, and you know that there's 4 quadrants, 4 times 3 is 12. So it makes sense that it's 1/12 of a revolution. Now, of course, you could also multiply 1 over 12 by 360 to get the 30 degrees. Please notice I've done that with all of our common angles. An angle of pi over 4 or 45 degrees is 1/8 of a revolution. An angle of pi over 3 or 60 degrees is 1/6 of a revolution. Pi over 2 or 90 degrees is 1/4 of a revolution. And then if I wanted to say, well, what about 1/3 of a revolution? That'd be your 2 pi divided by 3, or 360 divided by 3, 120 degrees. And then I kept on going on up all the way to 1 revolution there, you can see. Now, for the coterminal angles here, this is where I was talking about how 5 pi over 4 and 13 pi over 4 are coterminal because they have the exact same ending side. Any angles that have the same initial, which all standard angles will have the positive x-axis as the initial, but if the angle still has the same terminal side, regardless of the size of that angle, it's called a coterminal angle if it has the same terminating side. And now that's going to happen in degree mode whenever the coterminal angle is any increment of 360 degrees times any integer value k. So it could be, so k could be 1, 2, 3, 4, -1, -2, -3. So if I'm talking about an angle of, let's say, 120 degrees, well, 480 degrees is coterminal. Why? Because it's 360 more. I could add 360 again and get to 780. I know that that's coterminal to 120 because it's just 360 plus 360 plus that angle. So I could keep on adding 360 as many times or subtracting 360 as many times. In radians, you could add or subtract 2 pi radians as many times as you want, and each time the angle that you end up with is coterminal. Now, I accidentally stuttered with my A's here. In this one, for A, I was wanting you to find the coterminal angle that's less than 360 degrees. Usually I'll ask you to find the coterminal angle that's within the first revolution of the unit circle. So in this case, I want an angle less than 360 that's coterminal to 400. So you just say, well, subtract 1 revolution from it. The coterminal angle is an angle of 40 degrees, which we know is in quadrant 1. If I say I want an angle coterminal to a -135 degrees, that's between 0 and 360. So you say, well, just add 360 degrees to 135. You get your 225 degrees for that coterminal angle. What about if I have an angle in radian mode? Here I have 13 pi over 5. Please keep in mind 5 would go into 13 more than 2 times. So you'd say, well, it's 2 pi over 5 plus 2 pi plus 3 pi over 5, since there's that remainder of 3 pi over 5, that really already tells us what our coterminal angle is. But the main thing I was getting you to see is that this is beyond 1 revolution around. 10 pi over 5 would be 1 revolution around. So to get the coterminal angle, you just subtract 2 pi from it, and you can say, well, 13 pi over 5 minus 10 pi over 5 would give me a coterminal angle of 3 pi over 5 that satisfies my criteria up here of finding a positive angle less than 2 pi that's coterminal to this. So those two end at the same point. What if I wanted to find an angle that ends at the exact same point as negative pi over 15? And I need a positive angle that has that same terminating point. No big deal. I can just say, well, it's a circle, so if you add a circle angle around it, which is 2 pi radians, it's going to end at the exact same value. So we add 2 pi radians to that. 2 pi is the same thing as 30 pi over 15, so we can say 29 pi over 15 has the same terminating side of the angle as negative pi over 15. For example 10 here, I'm asking you, let me go back to this real quick. Remember, we was talking about circular arcs. If I wanted to talk about how to find the arc length of that circle, then all I would have to do is say the arc length S is going to equal whatever the radius is times the angle theta. Now, this S equals R times theta formula will always work as long as theta is given in terms of radians. If theta is given in terms of degrees, you're going to have to convert that degrees to radians before you can evaluate your arc length formula. So now, looking at an arc length formula here, says a circle has a radius of 6 inches. Find the length of the arc intercepted by the central angle of 45 degrees. Okay, now, typically that would confuse some people. They'd be like, well, what's going on here? I thought I was just using the formula S equals R times theta. You are. But please remember, you can't multiply by 45 degrees. That has no mathematical meaning within an equation. So when I do S equals R times theta, I'll say, well, my radius is 6 inches. Theta, can I multiply by 45? No. But I can multiply by the radian equivalent to 45. Now, you might already just say, well, I know 45 degrees is pi over 4 radians. Can I just put that in there? Of course. Or you could show it up here. 45 degrees is going to be 45 pi over 180. That's going to reduce down to pi over 4. So instead of placing 45 degrees in your arc length formula, you'll have to say R times theta in terms of radians, which is pi over 4. And then you say, well, that's going to give me 6 pi over 4. The arc length on the circle that's in this situation is going to have 4.71 inches. Now, definition of linear and angular speed. If I say if a point is in motion on a circle, so think about a point going around a circle of radius r through an angle theta in time t, its linear speed is, and this should make sense to you, it's just whenever we think of linear speed, it's the distance divided by time. So you say, well, the distance, that's the distance of the arc it's traveled. That's what S represents. S is the distance it's traveling on the arc, its arc length, divided by the time it takes. So the velocity is going to be S over t. Now, this is where the S is the arc length, like I just mentioned, and it's equal to that R times theta formula. And now its angular speed, if I just say, well, what is its angular speed? And this, it looks like a script W. It's called omega. Omega is equal to theta over t, where you just say, well, it's the angle traveled. So this should make sense. The angular speed. It's the angle traveled divided by the time required. Pretty explanatory there. So the angular speed, it's the angle traveled and whatever time it took. Now, the linear speed v of any point a distance r from the center of rotation is given by the velocity is equal to our radial our radius of our circle times this omega value, which is our angular speed, which says where omega is the angular speed in radians per unit of time. Now, let's look at an example of this because it's not nearly as complicated as what a lot of students would think after that. So notice here, I say long before iPods that hold thousands of songs and play them with superb audio quality, although iPods have pretty much gone away now. It's all phones. Individual songs were delivered on a 75 RPM or 45 RPM circular records, long time ago. A 45 RPM record has an angular speed of 45 revolutions per minute. We're supposed to find the linear speed in inches per minute at a point where the needle is 1.5 inches from the record center. Okay, now, whenever we're thinking about this, before applying the formula V equals the radius times omega, we must express omega in terms of radians per minute. So when I'm thinking about this, I can say, well, all right, it tells me up here that the record is going at a rate of 45 revolutions per minute. So I put over here 45 revolutions over 1 minute. Now, I know that that means in each revolution, so I need to get rid of revolutions. Each revolution is going to have 2 pi radians. So then when I'm thinking about, okay, what is this answer going to be measured in? It's going to be radians per minute. So do I want my do I want my omega value to be in radians per minute? Sure, that's exactly what I want. So I can say 45 times 2 pi, that's going to give me 90 pi radians per 1 minute, or just 90 pi radians per minute. Now I can say, when I go to the next part, the angular speed of, and it was 90 pi. I accidentally put 9 pi there. Forgive me on that. The angular speed of the record is 90 pi radians per minute, the linear speed. So if the angular speed is 90 pi radians per minute, because it's traveling 45 revolutions per minute, and each revolution you have 2 pi radians, so you say, okay, 90 pi radians per minute. Well, what's its linear speed? Its linear speed is going to be the radial length times that angular speed. So you just say 1.5 times this 90 pi radians per minute. And when we get that, we just say, well, 1.5 times 90 is going to give me 135. And this is going to be in terms of pi. Now it's in terms of inches per minute rather than radians per minute. And if you just multiply 135 times 5, you're going to approximately get that this is 424 inches per minute. Now, that will conclude section 4.1. Please do try the homework in this section. I think you'll find it fairly straightforward. Remember, I've worked all of the problems out of the book, and that should help you as you work the problems on my math lab to go back and compare it against what I did. But as always, if you have any questions, let me know. I'll be glad to help.